All right, guys, so what we looked at previously is we saw that we had an object starting with a mechanical energy of 50 joules, right? And then it became 25 joules. Then we said, okay, the only reason why mechanical energy would not be conserved or it would not be constant is because there's a non-conservative force that is removing that energy. Basically, a force that is doing work. And that force was frictional force. It removed 25 joules of energy. Now, I want us to get the terminology right. So we're saying frictional force removed energy, right? We saw that, we calculated it. But also another way you can state it in terms of work, because remember we said work and energy are the same thing. If frictional force removes energy, we're basically saying frictional force does negative work, of which it makes sense. It resulted in energy being removed. It did negative work. But let me explain it in a more simple way, right? Look here. Our object is moving to the right. But now frictional force, we know frictional force always opposes motion, right? Frictional force will oppose motion, which means frictional force will be acting to the left. So imagine you're running a race and you're trying to charge to the right. You're trying to run forward to the right, and someone just yanks your hair, right? Someone opposes your motion. That person is going to remove your energy because you're not going to be able to use that energy that you had to run the race forward. Now, this person that yanks your hair backwards, you're probably going to fall backwards. That's what frictional force does. It does negative work. You're trying to do work into the direction to the right, right? You're moving to the right. This box is trying to move to the right, but frictional force does negative work. It does work in the negative direction. It basically removes energy. So the two are interconnected. Doing negative work means you are removing energy, and that is what frictional force does, because it works in the opposite direction in which the object is trying to move in. Object wants to go to the right, frictional force says no, I want to oppose you, I'm going to try and pull you to the left. Okay, so forces that act in the opposite direction to the motion of the object will do negative work. They are removing energy. They're not helping this object move to the right. They're actually stopping it from moving to the right. Okay, and that's another reason why we say frictional force is a non-conservative force. It doesn't allow mechanical energy to be conserved. Now, I want us to look at other non-conservative forces, right? Because we don't just have frictional force. So, also, keep in mind, I said forces that act opposite to the motion of the object. So, forces that act opposite to the motion of an object will do what? They will do negative work. It makes sense. They're working in the negative direction. They're not doing what the object wants to do. Object wants to move to the right. Frictional force says no, I'm going to do the opposite of that. Okay, so any force that acts opposite to the motion of an object, it is doing negative work. It is going to remove energy. Now, let's look at applied force, right? So when you look at this applied force is being applied to the right at a value of 5 newtons. Now, they tell you that your object moves to the right, okay? So immediately I want you guys to now think of this. I said any force that is acting in the opposite direction to the motion of an object will do negative work. Applied force here is acting in the direction of the motion. So now imagine it like this. You're running a race with the energy that you have, and then someone just pushes you forward. You're definitely going to run faster and suddenly stumble, right? There will be more energy that you'll have. And that's what's happening here. The object is moving to the right, and applied force is being applied to the right in the direction that the object is moving in. So it's going to add energy there. And that's why you see your energy, your mechanical energy, goes from 50 joules to 75 joules. But let's calculate it. Let's actually prove that. Let's see that applied force does indeed do positive work here. It does positive work because it works in the direction of the motion of your object. So we said The formula for work done is force multiplied by displacement and cos theta. But we're specifically looking at the work done by the applied force, multiplied by the actual value for applied force, and then the rest. So our applied force is 5 newtons, multiplied by 5, multiplied by cos theta. Once again, you have to pause. Theta is not always 180. In the previous example with frictional force acted to the left. The motion of the object was to the right. That's why the angle is 180. Here, the object goes to the right and your force, your applied force, goes to the right. So the angle between those two is 0. Okay, and you'll check on your calculator, cos 0 will be positive 1. Eventually, you'll get an answer of 25 joules, positive 25 joules. And you can even go on and add that if it's positive 25 joules, it means that added energy, 25 joules of added energy. And that once again proves our point. Forces that act in the direction that our object is moving in will do positive work. That's why our answer is positive. But they will add energy too. Doing positive work means you add energy. And that's what we see here. But now I want to show you guys this. What if you have a situation? So here I was just saying, because applied force acts in the same direction as the object's motion, it does positive work. So it adds energy. But what if we have a situation like this? Same question, right? But now, object moves to the right, but our applied force is to the left. I know some of you are like, what? How can that even happen? Because applied force always has to be in the direction that your object moves. That's not true. That is absolutely not true, right? Because, for example, someone is basically trying to pull an object to the left. That's what's happening here. Someone is applying a force to the left. Their objective is to move the object to the left. But what if the frictional force is so strong that the object actually continues to move to the right? Okay. Or the applied force is not strong enough. There is an opposing force that doesn't allow this object to be moving to the left, because that's what applied force is trying to do. Or let me explain it like this rather, right? Let's say your object was initially moving to the right, okay? Your object is just moving to the right at 5 meters per second. Now someone applies a force. They're like, hey, I'm trying to stop this box from moving to the right. So let me pull it to the left. But maybe that's not enough force, right? So the object will continue in its motion to the right. That is why sometimes applied force will not be in the same direction as the motion of your object. I know you guys sometimes get so used to thinking, no, but applied force always has to be in the direction of the motion. That's not true, right? Applied force can be to the left, but your object continues moving in a different direction, okay? So, and the reason would be because you're not pulling it hard enough. Your 5 newtons is not enough to change the direction that your object is moving in. So now, let's calculate the work done by the applied force here. We'd say applied force multiplied by delta x multiplied by cos theta. It is still 5 multiplied by 5 multiplied by theta. And here, we check the angle, right? We're saying our object moves to the right, but our applied force is to the left. Angle between them is 180. So here we actually have cos 180. Then you guys will see your answer will be minus 25 joules. Basically, 25 joules with removed energy. And it makes sense because forces that act in the opposite direction to the motion of your object will do negative work. They will remove energy. So the point I'm trying to show you here is that in this question, this applied force is actually acting in the opposite direction, so it will remove energy. But still, they do the same thing. Mechanical energy is not conserved. Whether your applied force is acting in the same direction as the motion of your object, or your applied force is acting in the opposite direction to the motion of your object. Mechanical energy is not conserved.